Let's continue our discussion of passive sign convention by considering this circuit here where we have actual values as opposed to just variables. So we're not actually going to do any analysis on this circuit, but instead we can say the analysis was already done. So analysis was done and it is going to give us values for V1 and V2. So V1 was found to be 17.2 volts. And V2 was found to be 12.0 volts. And so what we want to find then is we want to find the current I. So two things. First is the current I in our 5 ohm resistor. And the second thing is we want to find the power associated with our current source. So power associated with current source. Okay, and so remember, we're going to of course be using our passive sign convention, which applies to our passive components as well as our sources. Okay, so if we want to come find the current in our 5 ohm resistor, we see that we don't have a voltage defined across that 5 ohm resistor. So how do we address that? Well, of course we can just define a voltage. So then the question becomes, which one do we want to define? We can define our voltage one of two ways, right? We can define it with the positive polarity on the left, like this, or we could also define it with positive polarity on the right. So I'll go ahead and do positive polarity on the right. What you might want to do for practice is maybe switch around the polarities and see if you get the same thing. So we can then relate, we know if we're looking for the current, if we find voltage and resistance, we can find current from Ohm's law. So that's kind of our game plan then, right? So we want to use Ohm's law, V equals IR. We're trying to solve for a current. So we know I equals V over R. So now we know R, we just need to figure out what V is. And so a technique that you should remember from 201, Applied Electrical Theory 1, is how to do KVL to find voltages. So in this case, since we already know V1, we're given the value of V1, and of course we know the value of that 15 volt source, what we can do is a KVL around this loop here. So sort of the bottom left window of this circuit, we can think about it, or the bottom left pane. And for KVL, remember, you can start at any point and go in either direction and you'll get the same result. So for instance, let's just say that we're going to start here and go in a clockwise direction around the loop. So what that's going to give us then, so let me come down here and we'll do sort of a little bit of a review. From KVL, let's put a dot here so we know we're working on this first one. From KVL, we would have negative V, because we see the negative of that V we defined first. So we have negative V plus V1, and finally minus 15. We came back to where we started, so we set that equal to 0. So one thing that I'm going to do more frequently as we get comfortable with this type of analysis, instead of initially writing negative V, what I'm going to do in my head is go ahead and move that negative V to the other side of the equation. So instead of writing it like this, I'm just going to go ahead and write, for the most part, V equals, and then continue around the loop. So I could say V equals V1 minus 15. So of course what we can do then is we substitute this in for our expression here. So now we have I equals V1 minus 15 divided by RR, which is the 5 ohm resistor. Now V was found to be as 17.2, so we just plug that value in. We have 17.2 minus 15 divided by 5, and so if we calculate that out, we'll see that gives us 400, well, let's keep it as amps first, so that would be 0.44 amps, and so we could represent that as 440 milliamps. So which unit you kind of depends on the situation and the value. So that would be our current. And so I do encourage you to try solving that with the polarity on that V just switched around to see that you would get the same answer. Okay, so now let's take a look at finding the power associated with that 3 amp source. So let me just put our circuit down here again so that we don't get too clustered up. Okay. So now we're looking for the power associated with this 3 amp source. So in this case, we have the current already defined. Our reference current is going down, but we don't have any voltage once again. So we have options. So let me get our same color here so we can either define a voltage like this, or of course we could also define it as being positive at the bottom, negative at the top. So I'm going to go ahead and stick with this last one again, but for extra practice you can try switching that polarity around to make sure that you get the same answer. Okay, so in this case we're talking about power. Remember, for a resistor we have multiple forms of our power equation. P equals I squared, P equals V squared over, I squared R, P equals V squared over R, or P equals IV, but because we're talking about a source, we have to use the P equals IV form. Okay, but we want to consider our passive sign convention. So we come here and we look at the reference direction of our current and the reference polarity of our voltage, and we see that it's going through a voltage rise. The current is going through a voltage rise. It's going from negative to positive, which means we're in that otherwise case, and we need to include a negative sign. So we know, of course, our current is 3 amps. We don't know the voltage, so again, we're going to have to do KVL. So we have a couple options. We can do KVL around any of these loops that include this voltage V. We could do this loop here. The issue is we don't immediately know the voltage across the 20 ohm or the 6 ohm. Of course, we could find it if we wanted to. We could do this loop here. Same issue where we still don't know the voltage across the 20 ohm. We could do this loop here where we could use the voltage we just found across the 5 ohm, but probably the easiest way is to just do this loop here where we are just dealing with V1 and the 15 volts again. So our KVL loop is essentially going to look very similar because if you notice closely, the 3 amp source and the 5 ohm resistor are actually in parallel. They share the same node pair. So we can write this KVL as, using that little trick I just talked about, if we start up here in this corner and we go clockwise around the loop, we get negative V, but I'm going to move it to the other side and say V equals plus V1 minus 15. So now we just plug that into our power equation. So we have P equals, and we have to keep that negative sign. Our current was 3 amps, and our voltage is V1, which was 17.2. So remember, that was given as already having been solved. And then we subtract from that the 15 volts. And so we get negative 3 amps times 2.2 volts, which is going to give us negative 6.6 watts. And so again, I would encourage you to work through that again with the voltage polarity flipped, just to ensure that you get the same result. So a couple of things I want to note before we finish talking about passive sign convention. One is note that we can choose these reference directions and reference polarities however we want while we're doing our analysis, but when we're asked for something that's already been defined in the circuit, we need to be careful to relate it back to that. So for instance, maybe we had been asked to define or calculate this current I. And so in that case, like we did with here, in our first part, we had to make sure that this final answer here matched the direction given for I in the circuit. Because if we have it going backwards, then that's not the same thing. So we could define a current going in the other direction. For instance, we could say, let's call this I primed, but then at the very end we would want to relate it back to this if the problem explicitly asked us to find I. The other thing I want to mention that hopefully you remember from Applied Electrical Theory 1 is related to our power. So for this case, we found that our power was negative, so power is less than 0, and that means that the source is supplying power to the circuit. If the power was positive, then that would mean that power was being supplied to the source from the circuit. Remember that resistors are always going to be absorbing power. Our sources can either absorb or deliver power. If there's only one source in a circuit, it has to be delivering power. But whenever we have multiple sources, at least one of them has to be delivering, but it's possible that some of the others are absorbing. So that concludes our discussion of passive sign convention. So hopefully now we're all sort of on the same page. But if you do have any questions, please feel free to contact me.